SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about natural convective flows over a vertical flat plate and few other geometries. Now, if we recall, in the last class we have derived the thermal boundary layer equation and the velocity boundary layer equation. Subsequently, we have derived energy integral equation and momentum integral equation for natural convective flow over a flat vertical surface which is at a higher temperature than the ambient fluid temperature. Quiescent fluid is at temperature T infinity, and this flat plate is at a temperature TW. TW is greater than T infinity, and this higher temperature induces thermal buoyancy and a flow field has been generated. So we have looked into the derivation of the equations, and then we have finally reached this position that ux, the characteristics velocity in the boundary layer, is given by c1 x to the power m, and the growth of boundary layer is given by c2 x to the power n, c1 x to the power m and c2 x to the power n. And then from our fundamental understanding we derived c1, which was found as 5.17 nu within bracket nu by alpha plus 20 by 21 enter quantity to the power minus half g beta theta m. Theta m is the maximum temperature difference, TW wall temperature minus T infinity divided by nu square to the power half, and C2 is 3.93 nu by alpha to the power minus half, then again nu by alpha plus 20 by 21, just like this parameter here, to the power 1 by 4, and g beta theta m by nu square to the power minus 1 by 4. So if we then substitute value of C1 and C2 in these two expressions, and also we have a priori found out value of m and n. M is half and n is 1 by 4. So we get the explicit expression in closed form for ux, which is 5.17 nu, Prandtl number plus 20 by 21. This nu by alpha we substitute with Prandtl number. So to the power minus half g beta theta m by nu square to the power half x power half. Similarly, delta equal to 3.93 Prandtl number to the power minus half, Prandtl number plus 20 by 1 entire quantity to the power 1 by 4 g beta theta m by nu square to the power minus 1 by 4 and x power 1 by 4. So these are the closed form solutions of the velocity field and the growth of boundary layer. Here of course, we have taken the boundary layer profile such that thermal boundary layer and hydrodynamic boundary layer or velocity boundary layer are same, and this is created because of thermal buoyancy, and mostly such flows are the fluids like air, due to the fluids similar to air, or the Prandtl number may be wherever it is very close to 1. Now delta by Ax is given by from previous expression of delta. If we try to obtain delta by Ax, then this terms will remain same. X will go as the denominator on left hand side, and this x power will be minus 3 by 4. So exactly that is what we get, and then delta by x equal to 3.93 Prandtl number to the power minus half, Prandtl number plus 20 by 21 to the power 1 by 4 g beta theta m, and we bring this x power minus 3 by 4 under this bracket, so it becomes x cube to the power nu square entire quantity to the power minus 1 by 4. Why we do this? We get Grashof number, and Grashof number is given by g beta temperature difference theta m length scale cube, here it is x cube by nu square. So we can get delta by x equal to 3.93 Prandtl number to the power minus half, Prandtl number plus 20 by 21 to the power 1 by 4, and Grashof number to the power minus 1 by 4. So delta by delta x we can write in a more compact way 3.93 Prandtl number plus 20 by 21 divided by Prandtl number squared and then Grashof number, this entire quantity under bracket and then to the power 1 by 4. So this becomes expression for delta by x, and we will remember this. Now in order to calculate heat transfer from the plate or the vertical flat plate, we define heat flux q double prime equal to minus k dt dy y equal to 0. This is at any x. So we can say hx into tw minus t infinity. So let us go back to geometry again. So basically we at any x location we can define hx, and hx is indicative of heat transfer from the wall to fluid. So Hx into Tw minus T infinity. The local heat transfer coefficient at any x location, we have already explained that this will be Hx equal to minus K del T del Y at y equal to 0 divided by Tw minus T infinity. So Hx is minus K Tw minus T infinity del Y of full expression for T, which is given by Tw plus Tw minus T infinity into 1 minus y by delta squared at y equal to 0 del y of this quantity, and we can easily see that this will give twice K by delta after this derivative. So Hx into x by k, if we try to get this expression, then this will be basically we can transfer k to left hand side and then multiply with x, we'll get twice x by delta. Now we know expression for delta by x, so twice x by delta, we substitute expression for delta by x and we get 2 by 3.93 Prandtl number squared, Grashof number, Prandtl number plus 20 by 21 to the power 1 by 4. So Nusselt number at any x from the leading edge is given by 0.508 into, within the bracket, Prandtl number square into Grashof number divided by Prandtl number plus 20 by 21, entire quantity raised to the power 1 by 4. This is the expression for Nusselt number at any x from the leading edge. The average Nusselt number over the plate is given by NUL over bar, which is basically, if the L is the plate length, integration between 0 and L, NUX dx, and then divide that quantity by the plate length, and this gives us 4 by 7 NUL. This NU is basically defined as in H into L by K. So Nusselt number based on plate length. So that means at the top edge, whatever is the local Nusselt number, that is NUL, NU into their x is L, H into L, x is L, H into L by K, that is NUL, and 4 by 7 of that quantity is average Nusselt number. L is the length of the plate. Now, in a field where free convection and forced convection both are present, free convection is negligible if Grashof number by Reynolds number square, Reynolds number arises out of forced flow. So if Grashof number by Reynolds number squared is much less than 1, and forced convection on the other hand is negligible if Grashof number by Reynolds number squared is much greater than 1. For a situation with combined free and forced convection, the condition is Grashof number by Reynolds number squared is of the order of 1. So we can write Grashof number G beta theta m L cube by nu square is of the order of u square. This u is forced flow velocity L square by nu square. And from here we get basically the free convective velocity scale, which is root over G beta theta m into L. Unit of theta m is basically temperature unit, Kelvin. Beta is 1 by temperature, 1 by Kelvin. These two cancel out. G is meter per second square multiplied by L, meter square by second square. Root over that is meter per second. So unit wise also it is matching, and our earlier definition of characteristics velocity also philosophically is the same, agglomeration of this, of the similar parameters or analogous parameters or the same parameters. So this gives basically expression for free convective velocity, how a free convective velocity or natural convection velocity can be created. If we know the volume coefficient of expansion, if we know the temperature difference in the field, if we know distance between 2 points through which this temperature difference is acting, and G, then we will be able to calculate natural convective velocity. So in the above expression, means earlier expression 25 is used for laminar boundary layers. It is customary to correlate the transition to turbulence if Rayleigh number crosses a certain limit. And Rayleigh number is basically Grashof number into Prandtl number. So Grashof number is G beta TW minus T infinity. We can say delta T x cube by nu square into nu by alpha. This quantity nu by alpha is Prandtl number. This is Grashof number. Grashof number into Prandtl number is Rayleigh number. So if Rayleigh number crosses 10 power 9, then flow becomes turbulent. Now, without going into basic derivation that we have done for laminar free convective flow, here we can give some important correlations. For vertical plate, average Nusselt number is given by this expression, which was found through carefully done experiments, and then try to find out a correlation to summarize all the experiments. And here you can see the expression is in terms of Rayleigh number, and Rayleigh number limit has been given. Similarly, horizontal plate, where characteristics length is given by surface area by perimeter, it is given by NUL bar equal to 0.54 Rayleigh number to the power 1 by 4. And again, range of Rayleigh number has been indicated. Long horizontal cylinder, we can say a horizontal long cylinder, Nusselt number based on the cylinder diameter is given by this expression, and here Rayleigh number is defined based on the diameter of the cylinder, and also we get Prandtl number here, and we see the range of Rayleigh number for this correlation. These correlations can be used for the practical applications when we come across similar or analogous flow situations. Now very quickly we will show, basically if we know the Nusselt number, average Nusselt number due to a vertical flat plate, then that can be related to average Nusselt number to a vertical cylinder. And how we can relate that? This is average Nusselt number for a cylinder divided by average Nusselt number for a flat plate, and this is a parameter zeta, which is given by 2 into root 2 divided by Grashof number based on the length of the cylinder to the power 1 by 4 into L by R, where R is the radius of the cylinder and L is the length. L is the length of the plate as well. So if finding out average Nusselt number for a flat plate is easier, and then we can link it to the average Nusselt number for a cylinder for different Prandtl numbers. We can see variation of Prandtl number is from 0.01 to 0.1 to 0.72 for air, to 1 to 10, and then we have also indicated here for Prandtl number equal to 100. High Prandtl number means basically these are flow of oil or similar fluids. Now we will touch upon mixed convection scenario. Mixed convection, here we have shown through a rectangular channel. Let us consider flow of air or other gases also we can consider through a horizontal channel as shown in the figure. Two important non-dimensional groups may be introduced here. One is Archimedes number AR and another is fluid number FR. The reference temperature is T infinity, which is basically quiescent fluid or outside fluid temperature, not quiescent fluid. Fluid is being pumped into it or being forced into it. So basically the fluid before coming in contact with the heated surface, temperature is T infinity and reference pressure is P infinity. And where it is passing through a duct which is heated, and the top wall and the bottom wall are heated at a temperature TW, and if TW is much higher than T infinity, then obviously because of high temperature gradient there will be natural convection together with forced convection. The fluid number is given by FR, which is basically V by root over GL, and Archimedes number is given by beta into TW minus T infinity by fluid number squared, equal to, we can say, beta TW minus T infinity into GL by V squared. In the above mentioned definitions, V is the velocity and L is the length scale. The Archimedes number is linked to Grashof number as well, and we can write Grashof number is Archimedes number into Reynolds number squared. So we write Archimedes number beta TW minus T infinity into GL by V square, and Reynolds number square is V square L square by nu square. We get Grashof number G beta delta T L cube by nu square. Now the this figure showed us the schematic of flow arrangements, and if we want to solve this numerically, we have to consider continuity equation by invoking Boussinesq approximation, where it remains divergence of V equal to 0. We are considering three-dimensional flow field, this V is vector quantity equal to IU plus I small v plus IU plus J small v plus KW. Now X momentum equation we can write del U del T plus V dot grad U equal to minus 1 by rho dp dx plus nu grad square U. Y momentum equation, Y is vertical direction and gravity will be acting in vertically in the negative direction. So we can write del V del T plus V dot grad operated over lowercase v equal to minus 1 by rho del P del Y plus nu grad square V plus G beta T minus T infinity. So buoyancy will be acting in the vertical direction opposite to gravity. Z momentum equation dw del W del T plus V dot grad operated over W equal to minus 1 by rho del P del Z plus nu grad square W. And energy equation is del temperature del time del T del time plus again V dot grad operated over temperature equal to alpha thermal diffusivity grad square T. Now if we non-dimensionalize the velocity quantities by reference velocity, length quantities by reference length, pressure by rho into velocity square, and theta is T minus T infinity divided by TW minus T infinity, and time T star non-dimensional time is expressed as T, the time divided by convective time, and convective time is L by velocity at the inlet. L by velocity at the inlet, this is the convective time. So T by convective time is T star non-dimensional based time. Reynolds number is inlet velocity into L by nu. So this flow, as we said, it is mixed convective flow, and the velocity at the inlet of the channel or duct is UIN. UIN is the velocity at the inlet, and this is pressure driven flow. But this flow character will be modulated when it will enter the duct because of temperature of the duct, and this is how then we formulate. So these are the non-dimensional quantities. Grashof number will be involved, which is given by G beta, temperature difference, length cube by nu square, and Prandtl number. So this is non-dimensional continuity equation, non-dimensional momentum equation in x direction, non-dimensional momentum equation in y direction. Here we can see, in addition to our known form, we have gotten Grashof number by Reynolds number squared into theta, and this is momentum equation. Momentum equation is having a term which has theta built in. That means this momentum equation is connected to energy equation. So this is a coupled situation. Then in z direction, momentum equation is this total derivative of w star equal to minus del p star del z star plus 1 by Reynolds number grad square w star. So this is momentum equation in z direction, this is in y direction, this is in x direction, and this is non-dimensional continuity equation, this is non-dimensional energy equation. Total derivative of temperature, non-dimensional temperature, equal to 1 by Reynolds into Prandtl, Reynolds number into Prandtl number, grad square theta. And this Grashof number by Reynolds numbers, Grashof number by Reynolds number squared, this term is called Richardson number Ri. So why I have mentioned this is a very interesting flow, and famous author of heat transfer textbook, Professor Incropera, and his group in Purdue University conducted plenty of experiments and theoretical analysis for this mixed convection flow scenario. And here we can see that the flow is in the horizontal direction, but on the basically the cross normal planes, we will be able to see vertical structure. And these are all, if we look at two side-by-side vortices here, this is experimental, this is theoretical, we will see the presence of counter-rotating vortices. So basically this is the geometry. That means at each cross plane we'll be able to see some such counter-rotating vortices in the channel. Then we can discuss another very interesting situation. This is a forced flow basically, but forced flow not at a very high velocity, and corresponding Reynolds number is within 100, but this temperature difference may be very significant. The temperature of the cylinder and the temperature of the flowing fluid. Now when basically temperature of the cylinder is greater than temperature of the flowing fluid, then the Richardson number is positive. And when temperature of the cylinder is less than temperature of the flowing fluid, Richardson number is negative. In the mixed convection problem shown in this figure, vortex shading, because this is forced flow, usually there will be vortex shading, and if it is in the range of 100, so vortex shading is expected, is found otherwise, but vortex shading is found to stop completely at a critical Richardson number. So normally, even if we consider isothermal flow, there will be vortex shading. Now, because of imposed, influence of temperature difference, that means when it is mixed convection scenario, it will change. But what we have written here, vortex shading is found to stop completely at a critical Richardson number. The forced flow Reynolds number is 100. And this we have done through, we have arrived at this conclusion through very carefully done computational solutions, which were also compared with experiment of one experimental group. So here, for everybody can think about it and try to explain why such a situation takes place. So this is a publication we have referred to. The complete analysis is available here, and graphically also we can show. You can see here for different Richardson number, these are negative Richardson numbers, up to Richardson number 0, we can see vortex shading is taking place. Even at Richardson number 0.1, we can see shading is taking place. But from Richardson number 0.2 onwards, that means 0.2, 0.5, 1, etc., we can see the vortex shading is no longer there, right? Vortex shading stops. So this is what we have explained earlier, that this happens, and obviously this is something very unusual, but as I said, that free convection, when it is superimposed with forced convection, plenty of interesting and novel features can be observed. And these are the isotherms basically, and these are for different Richardson numbers, and Reynolds number is 100, and this d by h, d means diameter, cylinder diameter, and h is basically gap between these two side walls, that is 0.25. So free convection has wide range of applications in cooling of electronic devices and also computers. That is very important. Some heat generating electronic components are cooled using a fan or a pump too. Small pumps or small fans we have noticed within the computers, especially desktops. Obviously larger computers, special cooling devices are there. Therefore, a decision has to emerge whether only free convection or mixed convection cooling is to be used for cooling of electronic components. The choice depends on the maximum allowable operating temperature of the equipment. The convection heat transfer rate from a surface at temperature Tw in a medium at T infinity as usual will be given by HAW into Tw minus T infinity. H is the heat transfer coefficient and AW is the surface area. Therefore, the surface temperature will be higher if H is low for the equipment. Free convection heat transfer coefficient is usually low. So that is why a decision has to be taken whether it will be augmented by forced flow. So free convection or natural convection is a preferred mode of heat transfer. Usually blowers or pumps are not needed for free convection, and as a consequence the problems such as vibration, noise, etc. can be avoided. Free convection is usually appropriate for cooling low power devices because it will be naturally cooled. It is very effective for the extended surfaces too. For the high power devices, blowers or pumps are needed to maintain the operating temperature below the allowable limit. For even if the power is even higher, for even higher power devices, in order to maintain the surface temperature below the prescribed limit, phase change cooling is used. Basically, heat pipes are used for such cooling devices. We will come to know about heat pipes in this course later. The rates of heat transfer in free or natural convection can be made much higher by operating the devices in the near critical or supercritical regions of fluids. In such regimes, small changes in temperature or pressure yield large changes in the fluid thermophysical properties. Significant change in the thermophysical properties of the fluid can bring about appreciable change in the rate of convective heat transfer. So free convection is a very important process, and many a times we can gainfully utilize this for cooling of electronic equipment and cooling of computers which are not very high power or power intensive computers. So we will stop here today. Thank you very much. Thank you for your interest.